Hello everyone, welcome to our final project presentation. My name is Zane and I contribute to the project by proposing this idea, sourcing the datasets, and implementing linear regression model, creating a timeline and editing this presentation video. Hope you like it. Next, my team member will introduce their responsibilities.
Hi everyone, my name is Shixian Chen, and I contribute to our project by conducting data preprocessing and exploration, contributing to the implementation and fine-tuning of the random forest model, which I'll introduce later, editing and refining the abstract, introduction, and conclusion section of the report, and finally proposing and defining the evaluation matrix to assess our model performance.
Hi everyone, I'm Zhao Weitong. I will present our findings on predicting car prices using the XGBoost regressor.
Hello everyone, I'm Jun. I'm responsible for support vector machine model to predict car prices for our project. I will talk about the Luster AI method, SVMS, particularly with the linear kernel, can be a powerful tool for regression tasks, leveraging their capabilities to model complex relationships in data.
So the used car market is dynamic and highly competitive, with price influenced by the factors like age, mileage, and manufacturer. Accurate price predictions are crucial because they can help buyers, sellers, and dealers to make informed decisions on price strategy and purchasing. However, mispricing can lead to serious consequences such as financial losses for the sellers or missed opportunities for buyers looking for a fair deal. This highlights the needs for reliable predictive tools. That's why we come up with these ideas. We want to develop a predictive models and capable of estimating the selling price of used car based on multiple features. So we will evaluate for machine learning algorithms, random forest, XGBoost, linear regression, and the support vector classifier. So these models analyze various car attributes, includes manufacturer, production year, mileage, and aging specifications to predict prices efficiently. To measure the performance of those predictive models, we rely on two key evaluation metrics. One is R squared. It will tell us how much of the variation in car price is explained by the model. Higher score means a better predictive performance. And the root mean squared error. It measures the average error between the predicted and actual car prices. And a lower RMSE indicate the more accurate predictions. And next, Guzheng will take over and introduce the linear regression model.
Okay, so in our project, we actually applied linear regression. Since linear regression is a popular statistical technique using machine learning to model the relationship between two or more variables. Like essentially, it calculates a straight line that provides the best fit between a dependent variable and one more independent variables. So in our car price prediction project, we use this linear regression to establish a baseline predictive model for car prices based on features such as production year, mileage, engine volume, and other factors. This method is simple and computationally effective. So on the right side, you can see the advantage of using linear regression. So it's computationally simple and does not require a lot of resources and make it suitable for straightforward predictive tests like our projects. And it also provides a clear understanding of how each input features impacts the outcome. So and also linear regression works well with large data sets and it's not computationally intensive. Last but not least, its simplicity also makes it suitable for online or real-time applications where quick retaining and prediction are required. And after data pre-processing, we actually split the data sets into training and testing subsets. We split the training subset of 75% and testing subsets 25%. We train a model and we actually evaluate the performance based on R square score and the root mean square error. So the R square score, it was also called the coefficient of determination. It measures how well the model explained the variance in the dependent variable. So we got 0.33. This means that only 33% of the variability in car prices could be explained by the model. And we think it highlights its limited capability in capturing the data's complexity. And for the root mean square error, it was around 13,000, which indicates a significant average of prediction error. So it also suggests that the model have difficulty accurately predicting car prices. So we feel like the reason why linear regression so the reason we feel our linear regression doesn't perform very well in our analysis was because the used car market is highly complex and the car prices was influenced by a multitude of factors such as brand reputation, mileage, engine size, fuel size, and many others, which interact with each other in ways that are not always linear. So linear regression, by definition, assumes a straight line relationship between variables, which limits its performance. The model was unable to capture non-linear relationship in the datasets. So in conclusion, we feel like linear regression can be used as a baseline model in our project to provide point of comparison for more advanced models. And it's also why more sophisticated models like random forest and XGBoost were ultimately more effective, with higher accuracy and lower prediction error. And next, my teammates will introduce you the rest of the models that we used for this project.
Hi everyone, my name is Shixian Chen, and I will introduce a random forest model that I implemented in our project. So first question, what is random forest? Random forest is a very powerful ensemble learning method used for classification and regression tasks. So what it does is that it will combine all the multiple decision trees together, as illustrated here in the plot on the left. So we can see here we have n decision trees, and each decision tree has its own result. So random forest will use majority voting or averaging to get the final result. So you can see here random forest is very powerful because it's robust to overfitting, especially compared to decision trees. So for my model, in order to achieve a good model performance, I also use grid search. So grid search is a method to find the best combination of hyperparameters for a machine learning model. So we can see here in the plot on the right, top right, suppose we have two hyperparameter 1 and hyperparameter 2. And for each hyperparameters, we have 3 optional values. So what grid search does is that it will test all the possible 9 combinations of hyperparameter values defined in the grid. And in the end, it will use the combination that leads to the best model performance. So I have also attached the code here that I use. So you can see here my hyperparameters are n estimators, max features, and also mean sample leaf. Okay, and then I'll talk about the result. So not surprisingly, random forest actually has the best model performance. So it has R2 score is 0.76 and RMSE is around 8,000. So we can see here the evaluation matrix showed that random forest captures 76% of the variance in the data. And the reason why the model achieves such a good performance is listed here. So first, random forest is capable to model complex and nonlinear interactions. Second, it is robust to outliers and noise. So because of this, it can handle anomalies in car price data without significant performance degradation. And lastly, it avoids overfitting. As I have mentioned before, it averages predictions from multiple decision trees so that it can balance bias and variance. And also in the end, I also use my model to conduct a feature importance analysis. So according to my model, it thinks that mileage, production year, and airbags are like the top three most important features in the car prediction task. Thank you.
Alright, so what exactly is XGBR? It stands for Extreme Graduate Boosting Regressor. It is a powerful algorithm that builds a strong predictive model by combining a bunch of weaker models. The key here is that each model is focusing on fixing the mistakes made by the previous one. This process helps XGBR handle complex data and nonlinear relationships very well, which is good for predicting car prices. It also dealing very well with the imbalanced data by assigning weights where needed. And also XGBR is super flexible. We can adjust the settings such as max steps, estimators, and the learning rate to get the best results. And it is include the regularization, which helps prevent the model from overfitting. So here is how it works. It begins by making a simple guess by predicting the average car price, and then it figures out how far off those predictions are from the actual prices. And then a new decision tree is trained to predict those errors, also called residuals, focusing on areas where the first prediction went wrong. And this new prediction is combined with the original one to improve the accuracy over time. So to prevent the model from become too complex and overfitting, XGBR uses regularization to tweak the learning rate to keep things stable. Right, so from the result, we can see XGBR achieve a R-square of 0.72 and an RMSE of 8,748.1. So it shows 72% of the differences in the car prices can be accounted by the features using in XGBoost regression. And however, it is less accurate compared to the random forest regressor. The reason could be XGBR's performance is sensitive to how we set its parameters, and the random forest, on the other hand, uses a simpler average method, make it more robust for the dataset. And XGBR's method of focusing on its residuals might have amplified some noise in the data, which will reduce the accuracy. And from the picture of feature importance in the predicting car price, it shows engine volume, gearbox type, and the airbags are key features, and each contributing significantly to the model's accuracy, whereas color and age have a minor impact.
Hi, let's talk about SVMS for our project. SVMS are good for producing and sorting data. They work well because they found the biggest gap between groups of data. This helps a lot with making correct predictions. We use the different kernel functions like linear to deal with the complex patterns in the data. Choosing the right setting for C and gamma is very important. C controls how strict the model is with errors, and gamma decides how much the model looks at data that is far away. However, the SVM did not do well with our data. The R-square value was negative, which means it did not understand the patterns in our data well. The RMSE was also very high. This shows that there was a big difference between what we predicted and what's actually happened. This could be because the data was too messy or had too many extreme values, which can make it hard for the model to learn. Maybe this setting we choose for the kernel and its parameters were not the best. It's also possible that our data was too simple or complicated for our data, which made it fit poorly. And I hope this gave you a good idea of how we use the SVM and the issue we faced.
Okay, so for the conclusion part, we can see here that random forest achieved the best model performance among all the 4 different models. And next one is XGB regressor. However, it's not as robust as random forest, as random forest has a more balanced approach to bias and variance. The third one is linear regression. So linear regression really struggled with handling the dataset's nonlinear relationships. And last one is support vector classifier, which is proved to be unsuitable for our car price prediction task. So the reason why random forest is very successful is that it effectively captures the nonlinear relationships, and it also provides us with feature importance analysis. So this can really help us understand how the model interpret the features and also make the prediction. So finally, we can see here the tree-based ensemble methods such as random forest and the XGB regressor really outperform the other linear models because they're able to handle nonlinearity and feature interaction.
As for our future work, we can work on explore alternative models such as gradient boosting models like CapBoost or LightGBM to improve prediction accuracy. We can also incorporate additional features. We can include microeconomic indicators or detailed car history to enrich the dataset and enhance model performance. We can also apply optimization techniques to future fine-tune model parameters for better results. And also we can use techniques to handle outliers and nonlinear relationship more effectively. And lastly, we can expand use cases. We can adapt the model for broader applications such as forecasting future car market trend or pricing strategies or dealerships. Thank you for watching.